Hi everyone, I'm Li Chang-hee from Oregon State University. Today I would like to talk about our work bidirectional alignment for domain adaptive detection with transformers. The goal of cross-domain object detection is to learn an object detector that can perform well on unlabeled target domain when the training and testing data distributions differ significantly. In this task, the source domain and the target domain datasets share the same classes, but the object appearances are very different in the two domains. Therefore, the detectors trained only on the source domain perform poorly on the target domain. As we can see from this example, the detector trained on clear weather dataset misses a lot of objects in the detection on this left foggy weather image. This performance degradation is caused by the domain gap between the training and the testing datasets. In this scenario, the domain gap is from normal weather to the foggy weather. Some other common domain shifts are synthetic image to real-world image, daylight to night light, normal camera to fisheye eye camera, and so on. Following the previous adversarial learning methods, we think the image and object features are composed of domain-invariant features and domain-specific features. And the goal is to reduce the domain gap between two domains, and this is also called domain alignment. We found existing transformer-based methods implicitly reduce the domain gap. The resulting aligned features are likely to contain both domain-invariant and domain-specific features. We seek to explicitly separate domain-specific features from domain-invariant features. In addition, these existing methods do not explicitly consider the domain gap of image patches and object tokens. In this work, we seek to align every image patch and every object token individually. Based on these two motivations, we proposed a model called BIDT, in which we design a token-wise domain-specific embedding at the image level in the encoder and at the object level in the decoder, as shown in this figure. Each image and object token consists of a domain-specific part and a domain-invariant part. Therefore, our goal is to explicitly learn to separate the domain-invariant features and the domain-specific features. We designed two attention modules to bidirectionally align two domains, aimed at reducing the domain gap in the domain-invariant features, but also increasing the domain gap in the domain-specific features, as we can see from this figure. Need to mention here, the two attention modules are seamlessly integrated in the existing deformable attention and self-attention. This is an example of a predicted domain mask from BIDT encoder. As we can see, the domain masks are focusing on those domain-related regions. Here are some quantitative results. The first two columns are from two state-of-the-art methods. The third column is from our BIDT, and the last column is the ground truth. As we can see, BIDT can detect objects that missed in the other methods, such as the bus in these two examples. Here is a comparison of BIDT with the state-of-the-art methods on the cityscapes to the foggy cityscapes domain shift. As we can see, BIDT outperforms other methods with a clear margin. In addition, BIDT is also compatible with the equity alignments and the self-training paradigm. Thank you for watching.